Hello! In the previous video, we learned that when one incident wave superposes with one reflected wave, a standing wave is formed. Now, what if many incident waves superpose with many reflected waves? What's going to happen? So we have such a setup here. We have a string that's fixed at both ends. So on one end is fixed to the vibrator and the other end is fixed to the pulley. What this vibrator does is to send out a very small amplitude wave. Very small amplitude. So when this wave travels and hits this end, it's going to reflect back. Then it's going to travel, and when it hits the vibrator, it's going to reflect back again. And again. Meaning we are accumulating many generations of incident and reflected waves on this string. So they are all going to superpose with one another, right? So what's the outcome? Well, the resultant wave is usually nothing much, zero. Why? Because all the incident waves are not in phase with one another. So most of the time you get a lot of destructive interference and the outcome is, well, nothing. The string will be very quiet. However, if the string is of the correct length and if the vibrator is sending out wave that's the correct wavelength such that when the wave travels, comes back and sets off again, if it sets off in phase with the wave that the vibrator is sending out, then we have what is called a resonance. Because all the many generations of incident waves will then be in phase with one another, and then when they superpose, you get a very dramatic standing wave. Meaning you see a very spectacular large amplitude standing wave on the string, as if the string is possessed by some spirit like that. So as an A-level student, you're expected to be able to figure out all these special resonant frequencies for any particular string. And it's quite easy really. The key is at both fixed ends, we must have a note. So note here and note here. So do you think the standing wave can have this wavelength? No, right? We need a note and a note here, no? But this wavelength is too long. What about this wavelength? That's also the wrong wavelength, yeah? For this wavelength, the standing wave needs a note here and a note here, but the string will not allow that. So clearly, the correct wavelength will look like this. So when the string is in resonance, you see a standing wave that's vibrating like that. Meaning there's an antinote at the middle here. So the dashed line is drawn to kind of like show the amplitude envelope of the standing wave. Now it turns out a string has more than one resonant frequencies because this wave will also allow us to have note and note at both ends here, right? So this standing will be having note, antinote, note, antinote, note. So it fulfills the conditions to have two notes at both ends. So if you're following me, then you realize that, oh, of course, there's a next one, right? This one with note, antinote, note, antinote, note, antinote, note also satisfies the conditions that we must have notes at both ends. So in fact, we have infinite number of possible resonant notes on a particular string. I often think of them as sausages. See? First, you have a long sausage, and then you have two not so long sausages, and you have three shorter sausages, 4, 5, and so on. So all these are possible resonance modes for a string of a particular length L. Now, can you see that the wavelengths are getting shorter and shorter? Because every sausage is half a wavelength actually, right? Remember, this is note and note, right? So the note to note distance is half a wavelength. So for this one, we can write lambda 1 is equals to the length of the string. What about this one? You got two sausages, right? So 2 half wavelengths is equals to length of the string. And then 3 sausages, 4 sausages, and 5 sausages. Now let's write all the wavelengths in terms of this guy's wavelength. So this guy's wavelength is lambda 1, yeah? So what about this guy's wavelength? It's shorter. How much shorter? It's exactly half of this wavelength. And this guy is 1/3, this guy is 1/4, this guy is 1/5. Actually, it's quite obvious, yeah? Here we fit one sausage, here we can fit 2 sausages. So this sausage must be half the length of this sausage, right? And so on. Quite obvious, huh? Now, what about the frequency? Now, if this standing wave has a frequency of f1, then this one must have a frequency of 2f1. Why is that so? Now you must realize that the waves travel at the same speed, yeah, regardless of which resonance it's doing. So v is equal to f lambda. So v is the same for all these people. So if your wavelength is halved, your frequency must be doubled. So since this guy has 1/3 the wavelength, it must have 3 times the frequency. And this will be 4 times and 5 times. Now let's talk about the naming convention. So of all the possible resonance modes, the one with the longest wavelength, so this one, yeah, is called the first harmonic. It's also called the fundamental. Now this one is called the second harmonic. So this one is called the third harmonic, this is the 4th harmonic, 5th harmonic, and so on. So basically, if your frequency is n times f1, that means you are the nth harmonic. Now, some people also use the term overtones, especially people who are doing music, yeah? So if you are the harmonic after the fundamental, you are called the first overtone. Then the next one will be called the second overtone, and the next one will be the third overtone, and so on. So it's quite fun, really. So most of the time you'll be doing sketches. Just keep filling the string with sausages such that you have notes at both ends so that you can figure out the wavelengths and the resonant frequencies. Alright, that's all. Ta-ta!